infinity is a very useful way of speech. When I don't like somebody, when I tell them to go to hell, doesn't mean I literally believe in hell. Sometimes ChatGPT faked it. So basically it's a faker, like students.
You're about to see an interview with the one and only Doron Zeilberger. Born in 1950 in Israel, he was kicked out of his high school because he dismissed all other subjects except math and physics. Despite that, he is now a distinguished professor in mathematics and winner of numerous prizes such as the Euler Medal, the Lester P. Ford Award, and several others. Professor Zeilberger is known for his unorthodox opinions, for publishing papers with his computer, and for his disbelief in the concept of infinity. In the interview, we will discuss all of this together with the religious beliefs of Doron Zeilberger, his memories of Paul Erdos, and other topics listed in the description below. Feel free to click on a specific topic there and to support this channel by subscribing. After the request of Professor Zeilberger, the actual interview is of length a little less than 52 minutes, which is roughly equal to 1 microcentury. More details about that in the first comment below. First, let me thank you, Professor Zeilberger, for agreeing to give this interview for the lesson on math. Let me start off by asking you about your mathematical work. Your areas of interests are combinatorics, special functions, and experimental mathematics, famously. When you say experimental mathematics, you mean, I guess, finding conjectures with the help of computers, but also letting computers solve problems themselves, right? This may sound to a lot of people a lot like some kind of machine learning, maybe, but I know this is not the case.
Yes, that's very thanks for asking me. That's really my pet peeve. In my humble opinion, experimental math will be, in other words, my style of experimental math will be the mainstream of mathematics in 30 years or even hopefully sooner. The mathematical community is still not ready for it. So they really don't understand the significance of this. So because of the advance of automatic theorem proving and machine learning, these are different approaches. It's not my approach. So I appreciate it. I know it's very challenging, but it's not my kind of math. Especially I dislike the attempt at so-called formal proofs of already humanly proved theorem. Somebody told me that recently somebody claimed a computer proof of Fermat's last theorem. I didn't have a chance to look at the details. Did you? So is that ab initio? Did it do it with using machine learning, that's from scratch, or it was parasitic? It just used otherwise and Taylor, I guess, proof and then quote unquote mechanized it. Do you know?
I'm not familiar with that. No.
My suspicion is the later, similar to the four-color theorem. I know it's a technically challenge, but I'm not impressed. The proof already existed. It was very convincing. The statements of the proof itself could be summarized in one sentence, and the rest is just the construction. There was computer aided and then computer verified. So I really don't, and no offense to Gontier, I don't think conceptually and philosophically and ideologically it's such a big deal. It's just an exercise in programming. Of course, it's very, very challenging, but I'm not excited about this.
Okay, but you're saying that your kinds of proofs using computers are different.
Yeah, right. So in other words, to put it in a nutshell, it's not the Greek tradition. Mathematics, unfortunately, is still under the influence of Euclid. Euclid was also a good guy. He did Euclidean algorithm, but he famously, and in my opinion, infamously, created the axiomatic method in which you take intuitively obvious statements and you made a very tedious thing that tortured high school students and also college students for many, many years in this very pedantic, very, very unappealing way of thinking. So I don't like automated theorem proving because it's based on the axiomatic method. It's logic centric. I am a fan of Al-Khwarizmi and the Indian, Babylonian, and Egyptian algorithmic, and Persian, of course, a algorithmic tradition in which you use algebra. That's why I like computer algebra. I like Maple so much, and of course also Sage and Mathematica, which are computer based on computer algebra in the tradition of Al-Khwarizmi, of algorithmically. And also Fibonacci, he was a Westerner, but he was an algorithmist and not in the tradition of Euclid that was a party line, unfortunately, still today.
I see, I see. So when you say Maple Mathematica, probably you refer to some symbolic computations. And
yes, the symbolic computations.
yes,
Yeah, but
can you give a simple example, maybe of some kind of problem that can be solved that way?
sure. Well, another pet peeve of mine is that for education, we take introduction to proof class in which they indoctrinate the students to use the mainstream current orthodox religion, the dogma of proof, lemma, and often the exercises they give them is just a waste of time. For example, one common exercise in Introduction to Proof course is prove that 1 plus 2 plus 3 up to n equals n times plus 1 over 2. And then it's very tedious proof, base case, and inductive hypothesis. It's logic centric. But it so happened that, and if one student thus does it empirically, he plugs it n equals 0, so the empty sum is 0, 0 plus 1 is 1, 0 plus 1 plus 2 is 3. So check it empirically for the first few cases. Of course, he gets 0 marks, and the professor will claim that he understands nothing about proof. But ironically, it's a completely rigorous proof, because in this case, they belong to, there is an a priori meta theorem that exists a number, in this case, the degree of the polynomial plus 1, that if you prove it in that many special cases, automatically it's a rigorous proof.
Yeah, I see. That's a very nice example indeed. You're actually using that the result of 1 plus 2 and so forth up to n must be polynomial, right? At degree.
Yeah,
right. Yeah, nice.
So to prove a two polynomial of degree d identical, you have to check d plus 1 special cases.
Right. Second question. You're known for publishing papers with your computer, Schauer-Biekhardt, named after your first computer in the 80s. You have said a long time ago that computers are soon going to be superior to humans when it comes to many tasks, including solving math problems. On the other hand, though, aren't the most promising ideas in artificial intelligence just trying to mimic the way humans approach some tasks? For instance, neural networks are just mimicking the way brain works. Given that said, my question is, do computers deserve such big credit in a way?
No, the point is the computation that in principle are routine, they're so important, and in the end, everything would be routine. So let me interrupt and maybe the tangent. Recently there was a special issue, two special issues of the Bulletin of the American Mathematical Society describing the computer revolution and how computer is going to influence mathematics. But this is going to be all obsolete in 20 years. The stupid humans, they only try to have their own agenda and use the computers as to further their own agenda. And some of it is dismissive of more concrete mathematics like combinatorics. And they try to define value and what's the central question in the style, maybe a little bit more less blunt, of Bourbaki over big snobs, abstract snobs, and look down on more concrete things. And so, ironically, all this will be obsolete. Gödel famously proved that there exist true but undecidable statements. This is a big misunderstanding. In my philosophy, what he proved was something even more interesting, that most statements involving the so-called infinity that were believed erroneously to be meaningful are really meaningless because they involve quantifiers of the so-called infinite sets. And this is infinite complete nonsense. Of course, it's a good, nice symbol, and it can make sense of a lot of things. You can make it symbolically and fanatistically. Another thing that Gödel proved that I think is much more interesting, that they exist decidable in the sense of Gödel statements that are very short with arbitrarily long proofs. And I think this is true for most statements. So at the end, not even computers will be able to get so-called Euclidean style rigorous proofs. They will be completely obsolete. We realize that most human knowledge, even computers won't be able to give a full proof. So it still remains to be seen whether P not equal to NP or the Riemann hypothesis are in this category in which there probably exists a proof, and there already exists a proof, but a heuristic proof, not a proof that would be accepted in the annals of mathematics. But in my opinion, it's already very convincing, but not a so-called rigorous proof. So this still remains to be seen. But it has to be a curiosity. We learn to realize that if a human can prove it, and even a computer with the current, I don't know about quantum computing, but I very doubt the quantum computer will be materialized. But most of statement will be out of reach, and we will have to compromise with heuristic or at best semi-rigorous proofs. And mathematics will become a science again, like it was before Euclid ruined it. And for the Egyptians, for Babylonian, was experimental science.
Here, since we're talking about the role of computers, I would like also to ask you about the recent developments, these popular softwares like AlphaZero and ChatGPT. Have you tried, say, ChatGPT yourself?
Yeah, I didn't, but a friend of mine did. Yeah, so one of the articles in this issues that I didn't like, but I like some of the articles, was how sometimes ChatGPT faked it. So basically, it's a faker. It's trying to fake it, like students. I have an example. Some students get an A, and they have no clue, but they just mimic. So in a way, students use this kind of GPT style, and often they'll get away with it. They get an A, but sometimes it's obvious that by one tiny thing is that they have no clue what they're talking about. They're just faking it. So my prediction is indeed they'll be able to fake from Andrew Wild's proof, possibly a better one. But once again, it's using the human heritage. They just try to mimic all the human heritage. So it'd be a nice exercise, be a very nice curiosity, be fun, but conceptually, and it will only be a curiosity in 20 years because it's so much. This model is just mimicking human reasoning, and human reasoning will be completely trivial in 20 years.
Okay, but when we talk about AlphaZero, we have a different case, right? There, obviously, we have more than just mimicking.
Right. Yeah, this methodology, right?
Right.
And indeed, this may also make my stuff obsolete.
Okay, and then another kind of related question. You wrote in the past several papers on combinatorial proofs, various facts, and yeah, I like them a lot as well.
Yeah, actually too. Yeah, when I was young, your age, I really liked them. I still like them.
Right. And here my question is, would you agree that it would be more difficult for computers to produce such combinatorial proofs compared to algebraic proofs?
Yeah, in a way, there's either often, and I have a few papers by the way, students, that you can take an algebraic proof and bijectify it. So, in some sense, they're the same, but that's different versions. There's something called involution principle. Often, when you do what my friend Adriano Garsia calls manipulatorics, you have to use a negative sign. So in this case, you have trouble. So famously, when they get first combinatorial proof or bijective proof of order Ramanujan identities, they invented the so-called involution principle. There's a little bit artificial and unsatisfying, but in principle, it gives you be able to translate a so-called, they call it analytic, but it's really algebraic proof into a bijective proof. And sometimes you have a ugly algebraic proof and you bijectify it, but when you do everything together, you get a very elegant proof. So that's another direction you can teach computers. Take an algebraic proof once it's formalized and to automatically.
So you're basically saying for computers, these two might be kind of the same because we can.
Maybe some dictionary between.
Yes, certainly they're more elegant.
I love combinatorial proof, as you do.
Next, I read in your interview with Joe Gallian, you made an interesting analogy between teaching and programming. And so in summary, the way I understood your words in that interview is that if you're a good teacher, then you're usually a good programmer and vice versa.
Yes, I still believe it.
But here, someone could argue that these two might be different because for humans, they comprehend better if you give them the intuition behind things, whereas computers, you should be.
Oh, yeah, that's a good point. Okay.
Yeah, but I agree that there is, of course, similarity. Yeah. That was an interesting perspective.
Yeah, that's a good point. But still, most teachers are bad teachers because they assume that the student knows more than they really know, and just keeps kept. Of course, the computer is opposite extreme. If you take it literally, you're going to bore the student the other way.
Right. Okay, so now we are getting to perhaps one of the most interesting parts of the conversation, your disbelief in infinity. So I know you don't believe in it regardless of whether it's actual or potential.
Yeah.
And in one podcast, you've said that it might be the case that after we try to add one to some very, very big number, it might be the case that we get back to zero, for instance. In other words, there is nothing that guarantees us that we can always add one to a number and then get a bigger number.
Yes.
Do you believe that it's more probable that we get back to zero in a cyclic way after a certain point? Or you're saying that we don't know what exactly happened?
Yeah. The other possibility is an overflow error in the big computer in the sky. And that's an open question. Yeah, of course, you have to take it with a grain of salt. This is a theological question. And once again, intuitively, I believe in God, but not the God of the Bible, a more civilized God. But this is a metaphysical and philosophical, metaphysical, and theological question. So infinity is a very useful way of speech. When I don't like somebody, when I tell them to go to hell, doesn't mean I literally believe in hell. As it's a way of speech. So I still use infinity as a symbol and as a way of speech. But my point is that all the mathematics, all the mathematics, at least the mathematics worth doing, and the one that is applicable to science and technology, you don't need that orthodox approach of analysis in which you have the actual infinity and the so-called real numbers. You can rewrite it. It's illogical. Of course, it makes sense as a game. If you put quote unquote in front of everything, then it makes sense. If you don't take it literally, the axioms are still, it's a finite thing, and you can still talk about it as a pretend game. But what's the philosophers call ontological, this is completely an open question and really meaningless one way or the other. But in my kind of calculus, you can make everything discrete, and when you make this big number sufficiently big, you can make it so big that it won't matter, and then instead of the real, actually you have a discrete line, so you have like Planck's constant but much smaller, and then differential equation became finite difference equations, and everything is finite linear algebra. And then ironically, when you actually in real life solve differential equations that came from the continuous condition in real life, because computers are digital and finite, you digitize it and you approximate quote unquote the differential equations with finite difference equations and then you get approximate solutions. Most differential equations, as I'm sure you know, are not solvable explicitly in closed form. So you use numerics. So in this case, the same thing is true for the genuine. There's no genuine differential equation. It's only an approximation. Symbolically, you can take the mass size h, which is tiny, 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 and pretend it's symbolic and let it go to 0, and then you get back traditional calculus. But you can teach a calculus to high school and first year students just using discrete math, and everything is finite. And
Right.
as far as applications, it will be the same thing, only better. Conceptually, it'll be much simpler. Technically, it will be more complicated because then you have to have the h. For example, when you talk to the students, the derivative of x squared into the limit x plus h point square minus x squared over h. So the derivative of x squared is not 2x, it's 2x plus h, where h is this fundamental Zeilberger constant, much smaller than Planck's constant.
Yeah, you have an article about this, right? The continuous calculus is the degenerate case of.
Yeah, right. I still stand by it. A long time ago.
Yeah, and since you mentioned real numbers, I know that you're saying that basically irrational numbers like root 2 or pi are not actual numbers, but like classes of algorithms, right?
Yes, that's very well. First, it's a symbol, and also it's an equivalent class of algorithms. There's many ways to compute intervals. So that's another thing. People use interval arithmetic for so-called rigorous proofs. So since real number is meaningless, is I say this number is between alpha, some rational number, and some rational number a little bit bigger, and then this, and all you can do rigorously is prove it's in interval. So you can do everything with interval arithmetic and only have rational numbers.
Basically, this limit introduced formally by Weierstrass and Cauchy, right? They were not an obstacle for Euler and these other guys to apply for applications, right? So
there's another pet peeve, and lots of things. For example, my good friend, frenemy, George Andrews, in his books, he offers when he proves something with generating functions, he puts this absolute value of q less than 1. For him, a power series is a convergent power series, but it's complete nonsense. The finitistic algebra of formal power series makes much more sense and everything. And lots of things what Euler did, and people thought it was non-rigorous, and they made fun of him, makes sense completely in the sense of so-called formal power series, but not in the sense of physics as a formal proof means non-rigorous, or not in the sense of this stupid automatic theorem prover that for them formal proof is fully rigorous using formal logic, but in the sense of algebra of formal power series. Well, so in this case, sigma n factorial times t to the power n goes from 0 to infinity, or even sigma n factorial to the power n factorial to the power n factorial. It makes perfect sense. And a pioneer was Peter Henrici, that I really admire. And also Paul, and in the context of Paul Redfield theory, and Tat, the great graph theorist, and my hero, Marco Berger, in the context of formal languages. Also were pioneers in formal power series.
Maybe just to complete the topic of infinity, one of the objections to infinity are the numerous paradoxes which follow if we accept infinity, right? Like Banach-Tarski paradox, or I think St. Petersburg paradox. So
right, good point.
So can you just say a few words about one of these paradoxes so that
they're complete nonsense. They're complete. No wonder, like Hilbert's Hotel is complete meaningless. But I hate to be political, and I really stay away from politics. But I started to have doubts about the existence of infinity. As you know, and I'm Israeli, but I'm really embarrassed how Israel reacted with such primitive revenge to the attack. So Hamas is infinitely bad, really, really infinite. What they did, nothing justifies using violence. I'm a pacifist. And then Israel retaliated and killed 30 times more than they killed. So there are 30 times infinity. But 30 times infinity is still infinity. So they are equally bad, both of them. I hope that they get to the senses and make peace and stop killing each other.
Yeah, of course, it's terrible. Yeah, but for the Banach-Tarski paradox, I think,
yeah,
as I read, it's the core of the paradox is that they divide the sphere in some parts, some of which are unmeasurable, and
right. That's also nonsense. So,
right.
so in a way, it's just a proof that infinity is nonsense. A sophisticated proof in this case. It's amusing, of course, yeah. But
can we say that these paradoxes are one of the main reasons for us to be against infinity?
and for me, it's intuitive. The obvious infinity is nonsense. So, yeah. So,
Yeah.
but it's a good way to supporting evidence for those who are still skeptics.
Kind of related to this, let's talk about computational complexity. And I'm aware that you don't like it very much, but can you elaborate a bit here?
No, this is not quite right. Yeah, the simple notion of computational complexity is fruitful. For example, proving that something is O of n log n as opposed to O, capital O of n square is a very big breakthrough. For example, a quick short. What I don't like is a very rococo stuff that it became with all these complexity classes.
So you probably find them artificial and far from reality, not concrete. Yeah. Then let me ask you about this recent paper of your friend Igor Pak, great combinatorialist. He associates existence of a combinatorial proof for a problem with that problem being in the complexity class sharp P. So this means for him that, first of all, combinatorialists don't know what a combinatorial proof is. So this was an attempt for him to give such a definition with complexity classes. And isn't this an example where complexity is actually useful for combinatorics? And before that, would you agree with this definition of him?
No, I like Igor a lot, and I appreciate a lot of his work. But this is just this particular thing is on the style of complexity theory that's trying. So I don't care for it, to be honest. So I cannot really comment on it. I don't quite understand what he did, but I don't care for it. Intuitively, I know what a combinatorial proof is. You mean bijective proof? Or
yes, bijective proof, yeah.
Well, famously, Abel has a nice article, What's an Answer? And he defined an answer to combinatorial problem, polynomial time algorithm, for computing it. So this is and that's a notion of a good use of the notion of complexity, which is not too fancy.
Another question that is slightly related to the previous one. Have you ever thought of working on more applied areas like theoretical CS or statistics or physics?
You mean theoretical physics?
Yeah, like through maybe at an earlier stage of your career, did you have some thoughts of maybe having as your main field not combinatorics or mathematics, but something more quote unquote applied?
Well, in a way, what I do is very applied enumerative combinatorics and using computers. Maybe I should have, but no. No.
Maybe for you and for your generation it was slightly different, but for nowadays for students early on it's very big question. Should I try to work on more machine learning and statistics, something that would be useful for industry, let's say, versus more pure stuff? So
yeah, sure. As long as it's interesting. If that's doing it for the sake of promotion and tenure, then it's not a good idea.
So your advice to these young students is to pursue their passion in the first place, right?
Yes.
Yeah. Next, I would like to discuss these statements of G.H. Hardy that I know you don't like, that mathematics is a young's mind game. Also, his division of mathematics to pure and applied. Can you discuss this?
Sure, I love to hate him first. When he said about mathematics is a young man's game, he was talking about himself. He was not able to be creative after a certain age, so he projected his own incapacity to everybody else. Some people that I know, especially in this century, kept producing very good mathematics. Yeah, so this is complete nonsense. And also maybe sociologically in the old days, maybe it was a kind of truth. But in principle, mathematics is everybody's game from 5 to 120. And also he was a big snob. He really thought he was like a pure snob. And ironically, the most interesting thing he did, in my opinion, is a Hardy filter that is very useful, and Hardy spaces are very useful in electrical engineering. And his pure mathematics is with very elaborate, ugly, hard analysis. It's very unappealing, and it's not at all beautiful. So I don't know what he was talking about. So often applied mathematics is much more elegant than so-called pure mathematics.
What I read was that he had a heart attack at age like 60 or 62, and that was so that's why his creativity declined, and maybe that's why he, as you said, his own incapacity led to that. But in his defense, I also read that he was a strong pacifist, as you.
He was not a bad guy, right?
Yeah. So but maybe here is a connection.
He was not a
snob. But like maybe because he was a pacifist, he was against so-called applied math during that time.
Oh yes, that's a good way to
recognize they
okay, I forgive him. Being a snob is not the worst thing you could do. Okay. And also he was a great mentor to Ramanujan, one of my greatest heroes.
Exactly. I think even Freeman Dyson quoted him in his lecture on this Ramanujan conference. I think the quote was something like, young men should prove theorems, but old men should write books, something like that, which at least says that he didn't exclude completely old men. So
okay.
Next, let's move on to the Fields medals. You like the Abel Prize much more, so
I like it better than the Fields medal. First, the Fields medal is only for young people, and that's age discrimination. And I think they both have the same flaws, is that they stress certain areas, currently fashionable areas, in the expense of other ones. Yeah, I like Abel a little bit better than Fields, because Sumerezi is more broad-minded, and applied people and combinatorics even got it. Yeah, so Abel Prize Committee is more broad-minded, and Fields medalists just become members of the committee, and it's just like staying elaborating and almost the stuff that people get Fields medal for. And that's very esoteric and not very interesting to me.
Right. And exactly related to the Snobbism in math you so much dislike. Actually, last summer, 2023, you gave a talk on the history of algebraic combinatorics. There you discussed this division of Gian Carlo-Rota to the superformal Bourbakist style algebraic combinatorics called Algebra 1 and the more intuitive Algebra 2. My question here is, first of all, why is this mathematical formalism so bad? And then when did you start being against this extreme formalism?
But speaking of this talk that I quoted by Gian Carlo-Rota, in hindsight, he may be turning in his grave, because algebraic combinatorics that he was championing when he gave his talk at the Taormina conference for Garcia, it deteriorated and became Algebra 1 again. And it's super abstract, and most of it is very boring. And they have this journal of algebraic combinatorics that then seceded and became that algebraic journal. So Gian Carlo would have probably rolled in his grave if he saw how detailed how it deteriorated into abstract Snobbism.
Right. But when you say Snobbism, maybe if we try to define it, it's like looking down on more concrete papers.
Yeah, concrete and computational things, as
Yes.
opposed to, it's also called it keywordism. That is, just look at the keywords of something fashionable can done loosely, and something come from abstract algebraic geometry that has apparently a higher prestige. And even though the paper itself is probably boring or not very deep, it just uses what's considered deep mathematics. Doesn't mean it's deep by itself. So yeah, that's called keywordism. And that's especially where the journal rejects papers that by quickly looking at the content, and then they decide it's not up to their standards, quote unquote.
Right. However, would you say that this formalism and trigger is never needed? Can you think of some specific cases where we actually need to approach some problem with some kind of rigor and more formally?
It did some good, but then it was taken too far. And now with computers, also way before computers, now with computers you can check things empirically. Of course, you have to know what you're doing. It's just because you check for the first 10 million cases doesn't mean that it's always true. So you have to use some standards.
Right.
Yeah. Take it back. It did some good, but it also
Yes.
did lots of harm. Okay.
I guess your emphasis is that we should focus more on intuition and concrete things. Okay. And maybe you saw this link that I sent to you by Arnold, Vladimir Arnold.
Yes. Arnold was a big character. Personally, he was very obnoxious person, but his philosophy I like and completely endorse.
I mean, he went even further, saying math is part of physics.
Yes, I completely endorse it. It should be opposed to the physical science, empirical and physical science.
Another quote I liked was that mathematics is the part of physics where experiments are cheap.
Yeah, yes, that's a good quote. Also, not always. Sometimes you need very big supercomputers.
Yeah, nowadays, yeah.
Yeah.
Now let's move on to some famous open problems. I know you like Riemann hypothesis, or at least the discrete version, and
because it's so simply stated, and not the usual version, but the one equivalent to it with the partial sums of the Mobius function, in other words, so-called Mertens function. This is something so concrete, and the heuristic proof is intuitively obvious. I also like the P not equal to NP problem because once again it's so simply stated, yet it seems to be very hard to prove.
But some of the other famous open problems you don't like that much because they're kind of more artificial.
It's simply stated. I like it. I like all the Koba conjecture. You can explain it to a 5-year-old.
Speaking of problems, like how do you pick your own problems and what distinguishes a good problem from a bad problem?
If you like it, if you are interested in it, and if it's concrete, well, it has to be concrete, then it's good. And if the answer is, if it's a conjecture to be a nice closed form formula for a combinatorial problem, for example, in my case, enumerative combinatorics, if it's something conjectured to be nice, explicit closed form formula, but it seems to be hard, then it's a fun.
When you said that, I remember you had an article called The Most Beautiful Formula in Math about this 3 to n minus 1 closed form expression for the number of the towers.
Right, this is the power n, right? Something that is not at all obvious, something so-called related to animals. Now, lattice animals is extremely hard and it's intractable probably, but then some simplified model initiated with Viano and his students in Bordeaux get a beautiful explicit formula to the power n. And I gave a talk about it and gave a whole paper and had some ramifications. And this is an example of a very attractive problem.
Let me also ask you about your opinions, famous opinions. You have mentioned a few times that some people think that you're trying also to provoke with these opinions. Is there any truth in that?
There's a grain of truth. Nothing wrong with it. Just because I enjoy provoking doesn't mean it's wrong. It's false.
What is remarkable about the opinions is that they're very written with very colorful language, and yeah, it's obvious that you really believe in these things and you're passionate about this, and maybe that's why they're that famous. Actually, do you spend a lot of time when you write an opinion, or comes?
No, it's more half an hour.
Wow.
No. First, I have to think about it. So when I do my exercise walk, I think about it. But when I actually write it down, no, more or less spontaneous.
Okay, and you're generally known for your waff with the unorthodox and unconventional approaches, and you appreciate some unorthodox thoughts and moves and approaches instead of
Yes, I was
yourself.
like the underdog. Yeah, I never vote for the main candidate. I went for the Green Party, or somebody had no chance.
Oh, I see.
Right?
There is no particular reason or like.
No, that's like the underdog.
Okay, and towards the end, we may try to play a quick game where I will just tell you some famous mathematicians that you might have met, and you will tell me your memories if you met them, your general impressions. So, first, Paul Erdos. Have you ever met him?
Yes, several times. The first time was not that unpleasant. I was 27 and a half or 28-year-old in Georgia Tech, and I was one of my several postdocs was at Georgia Tech, and I was all eager to tell him about my recent results. And first he was friendly, but then he fell asleep, and the host apologized that usually he takes these pills, whatever it's called, barbiturates, and he forgot to take him this morning, so he fell asleep. But I met him several times after this, and he was always very kind and encouraging. And I kick myself. Some people talk to him for 2 minutes and they put him on the paper, and he was very liberal. People putting his name on the paper, and I could have, because I talked to him, but I didn't. So my eldest number is not 1, but only 2. But yeah, but he was always very nice, and he loved babies, and yeah, he was a good guy. I really liked him.
I know that he called children epsilons, right?
Right, yeah. He was a real mensch, a real good guy. And yeah, I met him shortly before he died in one of the last conferences when Herb Wilf was 65, I think, and he was there, and I talked to him also, and he was in very good shape. Was very sad when he died a few months later.
I see. The next person is John Nash. I know you've met him because he spoke at Experimental Math Seminar, but what do you remember?
Yes, and I used to bump to him when I commuted, taking the shuttle from Princeton Junction. He used to, after he got the Nobel Prize, he got an office at Princeton as a visitor, permanent visitor, although without pay. And he used to commute from his home in Princeton Junction to Princeton, and I used to bump into him and talk to him from time to time. He was very kind, and he did apparently he did like the so-called WZ method, WZ theory, because according to his biography, when they came to tell him that he's gonna get a Nobel Prize in economics, I think it was 1993. It was right after the talk of Herb Wilf in the Princeton combinatorics seminar, where he talked about the so-called WZ method. And so maybe that's why he liked Wilf and me. And he came to my, even though he was not invited, he came to my 60th birthday conference 14 years ago. And yeah, he was a great guy. Yeah, and also he was very, very good father. His son, also called John Nash, was also brilliant. He has a PhD from Rutgers under Mel Nathanson, who was at the time the Rutgers faculty. And he was also a chess master. He was brilliant. Unfortunately, he inherited the mental problems, and when he turned shortly after his PhD, he became mentally ill and could no longer do mathematics or anything for that matter. And he came when John Nash came to give a talk in my seminar. He brought his son, and during his talk, his son occasionally screamed, and people just ignored it. And after that, when we went for dinner in a restaurant, he also came along, and John Nash teased his son good-naturedly. I heard you made some comments during my talk, and so he was a very good father.
Good. And next is Gian Carlo-Rota.
Yeah, he's my hero. Really, he had very strong opinions, but his kind of combinatorics, even though he was a little bit abstract, I did like his style.
Have you met him?
Yeah, several times. And Rota had a good intuition of what, quote unquote, really important. Even though sometimes he was wrong. So yeah, so Gian Carlo-Rota I really liked. Although he did have strong opinions, and sometimes he was not very tactful, and in his memoirs, sometimes he offended people. He also was a philosopher.
And another hero of yours, as far as I know, is Adriano Garsia, right?
Yeah, I really like him, and I really like all his work. His combinatorics at its best. Although some of it is a little bit abstract, but still, it is algebraic combinatorics in the good sense of the word. Also, the Garcia-Milne algorithm is very useful, was very nice at the time.
The involution principle?
Right.
Okay, and then I noticed you mentioned Freeman Dyson several times in your opinions. What do you remember from your interactions with him?
Personally, I only met him twice, I think. Once in the Ramanujan conference in 1987, where he gave a great talk about Ramanujan's garden. And yeah, one of my earliest successes was proving the Q analog of the Dyson conjecture. And he would give, after I sent him the paper, the preprint, he gave me a very encouraging letter, very, very kind, that it was really a breakthrough. So it was, and then much later, he gave a talk in a seminar, and we drove together to the restaurant. And it's still, unfortunately, not recorded, but the abstract is still there. He didn't quite understand what experimental math was. He thought it was something related to experimental physics. So we have to tell him. But then he gave a very good talk. And also is the mathematical physics mafia of Rutgers wanted to snap him and come to dinner. But he said, no, this is a different seminar. So he refused to meet the Leibovitz crowd because he wanted to not to take away from our time.
Okay, so he spoke at the seminar, and then John Nash also talked. Yeah.
And so did you.
Yeah, okay. Just 2 or 3 more people. Terence Tao, have you ever talked to him?
Not one-on-one. I went to his talks a few times, and of course he's a genius.
Timothy Gowers?
Oh yeah, in Timothy I knew pretty well, and I like his little book, What is Mathematics, something like this. Or very short, mathematical, very short introduction. Yeah, he's a great commentatorist, and even though he doesn't use computers, I like what he does, and he's a nice guy.
Okay, and my second to last question is about religion. And I noticed in your opinions, you occasionally use expressions like religious dogmas or religious...
No, it is a metaphor for
sects.
The religious fanatism of the mathematical religion. No implication about the true religion.
Yeah, sure. But still, using these expressions suggests that maybe you know, have some opinions on that, and important question for you, perhaps. It just when someone reads your opinions, it seems that on one hand you criticize believing religiously in something, or
no, on your organized religion or established religion. But reason by itself is a very good sentiment. And I do believe in some kind of God. Not the God of the Old Testament, definitely. He was a barbarian, and not even the God of the New Testament. He was much, much more civilized and nicer. But still some kind of God. I'm sure there is a God, but I have no rigorous proof for that.
What's the issue with organized religion exactly?
Well, it condones lots of things. For example, eating meat, I think it's a big sin. So in my religion, in my God, it's a big sin. And my wife always gets mad at me when I say that slavery was terrible, or homophobia is terrible, and sexism is terrible, but it dwarfs, and people used to get shocked when it dwarfs against the sin of slaughtering innocent animals and eating them. So, and I know this is, and she always tried to poo-poo it, and she gets embarrassed when I say it, but I still believe in it. That's why I cannot get so passionate about all the world issues, about people, because next to eating meat, many things dwarfs. So I cannot be that so hard on people who eat meat. But my God, it's a sin. It's a very big sin to eat meat.
Good. And my last question here is about one very elegant proof of a popular theorem that you mentioned. Once you said that a mathematician can immortalize himself by giving a very elegant proof of some popular fact. The example you gave was this ingenious one-page proof of the Sperner's lemma by David Lubel.
Yeah, it was a beautiful proof. There are many other examples. The sensitivity conjecture that it was inspired by conversation with my colleague Mike Sachs, and the so-called Stanley-Wilf conjecture. They all were big open problems that at the end only had half a page or at most one-page proof. Yeah, so this is the kind of thing I really like.
And but you even said that in that way, this person, David Lubel, he immortalized himself.
Yes. Yeah, I agree. Yeah.
Is there some other way to immortalize yourself?
One way.
That's one way, yeah, okay.
If you prove the Riemann hypothesis, even the proof is 1,000 pages.
So is this one reason math is so appealing, that the results you prove are kind of eternal?
Yes, especially combinatorics.
Okay. Well, thanks very much for having patience.
Yeah, thank you for doing it. And I really enjoyed your interview with Bruce Bernd. I'm going to his conference together with Andrews next week. So it was really very interesting. Keep up the good work. You have very good questions.
Thanks. I try to go more in depth.